Bismillahirrahmanirrahim. Assalamu alaikum, students. Last time we discussed the idea of entropy. We justified that this thermodynamic variable, which denoted by S, we justified that it exists. We also justified that it is a state function, and we showed that the change in entropy between any two states I and F, that is SF minus SI, is equal to integral ds I to F, which is in turn equal to I to F dq by t, where dq is the amount of heat that enters the system and T is the absolute temperature of the system. And important here is that this integral on the right hand side is evaluated over any reversible path connecting these two states I and F. So it is for reversible process, right? So now what we do first, we will together take a sample problem to understand the idea of entropy fully. The sample problem goes like this. A lump of ice whose mass m is 235 grams melts reversibly to water. The temperature remaining at 0 degrees Celsius throughout the process. What is the entropy change for the ice? The heat of fusion of ice is 333 kilojoule per kg. I repeat the question. A lump of ice whose mass m is 235 grams melts reversibly to water. The temperature remaining 0 degrees Celsius throughout the process. What is the entropy change for the ice? The heat of fusion of ice is 333 kilojoule per kg. So phase change is taking place in this problem. Ice is melting to water, and you know phase change takes place at constant temperature. That temperature is 0 degrees Celsius, and it is said that this process happens reversibly, so we can make use of this equation to get the entropy change of ice. Its final state is water, initial state is ice, and it's also given that the heat of fusion of ice, because this process is called fusion, if the phase change takes place from solid phase to liquid phase, such a process is called fusion, and heat of fusion of ice is 333 kilojoule per kg. You must be knowing it. That means to melt 1 kg of ice to water at 0 degrees Celsius, you need to supply 333 kilojoules of heat. So let us solve it together. Solution. The requirement that we melt the ice reversibly means that we must put the ice in contact with a heat reservoir whose temperature exceeds 0 degrees Celsius by only a differential amount, thereby melting only a small bit of the ice. If we then lower the reservoir temperature by the same differential amount, the melted ice would freeze. Thus, the process is reversible. Now, for such a reversible process, for such a reversible process, we can write S water, which is my SF final state, minus S ice is integral dq by T. Now, since during process the temperature stays constant, so I take temperature outside the integral and inside is only dq. Now here dq means the small elements of heat energy that enter the ice from the heat reservoir, and the total of all these elements is just the total heat absorbed by the ice. So it is simply Q by T. Like Q is what? Q is the total heat absorbed by ice from the heat reservoir. Now this Q is ml. This equation, you know, the Q is the amount of heat put into the ice, m is the mass of ice, L is its latent heat of fusion. So mass of the ice is given to 35 gram. I write it in kgs, that is 0.235 kilograms. And I multiply it by the latent heat of fusion, which is given to be 333 kilojoules per kg. When you solve it, this turns out to be 7.83 into 10 raised power 4 joules. You know, 1 kilojoule is 1000 joules. When you make the calculation, you need to consider that. So it turns out to be 7.83 into 10 raised power 4 joules. Thus, as water minus S ice is Q by T. Q is 7.83 to 10 raised by 4 joules, and temperature is given 0 degrees Celsius, but you have to convert it into kelvins because this T here in this equation is absolute temperature, that is temperature in kelvins. Now 0 degrees Celsius is equal to 273 Kelvin, right? So when you make the calculation, it turns out to be 287 joule per Kelvin. 287 joule per Kelvin. So this answer completes our analysis of the entropy change of the system. Here ice is my system. Now we can carry the problem a bit further and consider the entropy change of the environment as well. In this case, the environment is the heat reservoir from which the heat required to melt the ice is drawn, right? Now, every unit of heat that enters the ice must have left the reservoir. The temperature of both ice and reservoir being the same. Therefore, the entropy change of the reservoir is equal in magnitude but opposite in sign to that of the ice. Or I can write delta S, change in entropy of the reservoir, is equal to minus 287 joule per Kelvin, right? So the entropy change for the ice plus reservoir taken together is the zero. I write the entropy change, when you add these two entropy changes, you will get zero. Entropy change for the ice plus reservoir taken together is thus zero. Right? This is true for any reversible process. You must remember it. This is true for any reversible process, right? Because any increment of heat that enters the system must originate from an equal increment which will be negative that leaves the reservoir, right? So let us move to our next topic. My next topic is entropy in case of irreversible processes. Right? We already said that this equation delta S equal to I to F dq by T describes the calculation of the change in entropy for a reversible process. However, there are no absolutely reversible processes in nature. Friction and unwanted heat transfers are always present. So every thermodynamic process is therefore to some extent irreversible process. The question is how to calculate the entropy change for an irreversible process. For that, what we do, we take advantage of the fact that entropy is a state variable. I write, we take advantage of the fact, that entropy is a state variable, right? That means the difference in entropy between states I and F is independent of the path we choose from I to F. So even though nature may have chosen an irreversible path between I and F for the actual process, we can choose any convenient reversible path for the calculation of the entropy change, right? So I write, must remember it, to find the entropy change for an irre for an irreversible path between two equilibrium states. Find a reversible path or process connecting the same states, and calculate the change, using equation A. This is my equation. I repeat, to find the entropy change for an irreversible path between two equilibrium states, find the reversible path or process connecting the same states and calculate the entropy change using equation A. Right? Why we can do so? Because entropy is a state variable. Right? So we consider an example. Let me use this color. So we consider an example for this. My example is irreversible heat transfer. We take the case of irreversible heat transfer and we see how to calculate the entropy change. Let me draw a figure first. complete the figure and I will explain to you. So I have completed my figure. So idea is like this. In part A of this figure, this is my figure A. In part A of this figure, I have two blocks which are at different temperature, individual temperatures. Temperature of this block is T1, temperature of another block is T2, right? The blocks are at different temperatures in individual insulating enclosures. These are adiabatic walls. They are insulated individually from each other thermally, right? This is my initial state in part A. Two blocks at different temperatures in individual insulating enclosures. Now my final state shown in part B of the figure, what I do in this situation, we remove the insulating wall between the blocks. So this insulating wall between the blocks is removed and they are allowed to come to equilibrium at the intermediate temperature TE. So TE is the intermediate temperature. So we remove the insulating barrier or wall between the blocks and the blocks are brought in thermal contact with each other to come to equilibrium intermediate temperature TE, right? Now we assume the blocks have the same mass m. So we assume the blocks have the same mass m and specific heat C and specific heat C, right? That will simplify our calculation, right? When we remove the insulating barrier that separates the blocks and bring them into thermal contact as shown in figure B part of the figure, they eventually reach the common equilibrium temperature TE. Now, this process is totally irreversible because we lose control once we place the blocks in thermal contact with one another. But to find the entropy change in this irreversible process, we choose a reversible path that leads us to to the same final state, right? To find the entropy change in this irreversible process, we choose a path, reversible path that leads us to the same final state, right? So let us do that. Consider first block 1. Consider first block 1 at initial temperature T1, right? Assume this to be the lower initial temperature. Assume this to be the lower initial temperature. Lower initial temperature, right? That means we assume initially that block 2 is at higher temperature that block than block 1, right? We can imagine a series of thermal reservoirs at temperatures. Imagine a series of thermal reservoirs at temperatures T1, T1 plus Tt, T1 plus 2 dt, so on. It will be in this series Te, the equilibrium final temperature, minus Tt, and finally Te. So we're imagining a series of thermal reservoirs at these temperatures, right? So start with block 1 in contact with first reservoir and then move it one step at a time along the sequence. Now at each step an infinitesimal amount of heat dq enters the block. The process is clearly reversible. How? Because at any point we can move the block back to the previous lower step and the same amount of heat dQ will flow from the block back into the reservoir. Now each reversible heat transfer dQ can be expressed as, then write dQ as mc dt, right? And thus we can use the equation, this equation A, because we are using the reversible path. So entropy change, let me use another color. So entropy change for block 1, which I write delta S1, is simply integral I to F dQ by T, which is equal to MC integral T1 to TE, T1 to TE, because block starts with temperature T1 and ends with temperature TE. Inside the integral I have dt by T, right? So this will be MC natural logarithm of TE by T1, T by T1. I name this equation. Let me use this color. Equation 1. Is there any equation 1? No. This is my equation 1. So we have calculated the entropy change for block 1, right? We can similarly construct a descending series of reservoirs for block 2 between temperatures T2 and T, and we can find the entropy change for block 2. So the entropy change for block 2, say write as delta S2 is MC integral T2, initial temperature of block 2 is T2, and final equilibrium temperature of both blocks is T, dt by T, which will be equal to MC natural logarithm of T by T2. Let me use this color. So this is, say, TE. So this is the entropy change of block 2. I name it equation 2. MC natural logarithm of TE by T2, and this is the entropy change. Equation gives the entropy change of block 1. The total entropy change, I have to add these two. The total entropy change is delta S. Let me make it clean. I use another color. Let me use this color. The total entropy change delta S is equal to delta S1 plus delta S2 is equal to MC ln TE by T1 plus MC ln TE by T2. MC ln T by T1 plus MC ln T by T2, which will be equal to, check it, MC ln Te square by T1 T2. This is my total entropy change. This is my equation 3. So I name it equation 3. So total entropy changes MC ln T square by T1 T2. Now if T1 is the lower temperature, then delta S1 is positive, it is greater than 0, and delta S2 is negative, that is less than 0, right? T1, if T1 is lower temperature, then delta S1 will be positive and delta S2 will be negative. Now we can show that the total entropy change delta S is always positive. I said we can show that the total entropy change delta S is always positive, for which we need to show that Te square by T1 T2 is greater than 1, because total entropy change is given by this expression. Now MC is always positive. Now this natural logarithm can be positive or negative. Now if this T square by T1 T2 is greater than 1, logarithm will be positive and change in entropy will be positive. So to show that total entropy change is always positive, we need to show that T square by T1 T2 is greater than 1. Now we first find, to do this, we first find the equilibrium temperature by requiring that the total heat transferred is 0. See, this system is outside insulated thermally, so total heat transfer must be 0. So we find the equilibrium temperature by requiring that this condition is fulfilled. Which condition? Total heat transferred is 0, that is Q1 plus Q2, which is MC Te minus T1. Q1 is what? Heat absorbed by block 1 plus MC Te minus T2, right? Where Q2 is heat absorbed by block 2. Remember, both blocks have common final temperature T. T1 is the initial temperature of block 1. T2 is the initial temperature of block 2. So we equate it to 0. When we solve this, we get Te is equal to T1 plus T2 by 2. So T will be arithmetic mean of T1 and T2. Now we write the quantity, we write the quantity T square by T1 T2 as, we can write T square by T1 T2 equal to T1 plus T2 square by 4 T1 T2. Check it. T square by T1 T2 can be written as T1 plus T2 whole square divided by 4 T1 T2, which in turn is equal to 4 T1 T2 plus T1 minus T2 square. 4 T1 T2 plus T1 minus T2 whole square divided by 4 T1 T2. Check it. Which will be equal to 1 plus T1 minus T2 square over 4 T1 T2, right? 1 plus T1 minus T2 square plus 4 T1 T2. Clearly, this thing is, this quantity, this whole thing, right hand side is greater than 1, because the last quantity is positive always. T1 minus T2 square by 4 T1 T2 is always positive. Now T2 square by T1 T2 is 1 plus something which is always positive. That means in turn that T2 square by T1 T2 is greater than 1 always. It is greater than 1. So when it is greater than 1, that means total entropy change is always positive, because the logarithm of greater than 1 quantity is greater than 0, and the entropy change is positive. So we showed this total change in entropy, this total change in entropy is always positive. That means what? That this total change in entropy, the entropy always increases. Change positive means the quantity always increases, right? So placing the two blocks in thermal contact produces no change at all in the environment. So delta S is 0 for the environment. Environment. Why? Because the two blocks are externally thermally insulated. So I'm saying placing the two blocks in thermal contact produces no change at all in the environment. So delta S is 0 for the environment. The total entropy change, the total entropy change of system plus environment total entropy change of system plus environment, right, is always positive for irreversible heat transfer. System and environment is positive for this irreversible heat transfer. That means the total entropy of the system plus environment for this irreversible heat transfer always increases because the total entropy change of system plus environment is positive, right? Now I give you homework problem. Homework question goes like this. Says a piece of ice of mass mi equal to 0.012 kg is initially at a temperature Ti equal to minus 15 degrees Celsius. It is dropped let me make it clear. It is dropped into an insulated container of negligible heat capacity containing a mass mw what 0.056 kg of water at a temperature Tw equals 23 degrees Celsius, right? The system comes to equilibrium at temperature Te. Calculate the total entropy change of the system plus environment use the following specific heat capacities capacities and heats of fusion CI 2220 joule per kg Kelvin, CW 4190 joule per kg Kelvin, L 333 kg per kilogram. So let me check the question again. I repeat it. A piece of ice of mass Mi equal to 0.012 kg is initially at a temperature Ti equal to minus 15 degrees Celsius. It is dropped into an insulated container of negligible heat capacity containing a mass Mw of Mw equal to 0.056 kg of water, right? At a temperature Tw equal to 23 degrees Celsius, the system comes to equilibrium at temperature Te. Calculate the total entropy change of the system plus environment. Use the following specific heat capacities and heats of specific heat capacities. This is and heat of fusion. Let me bring my pen back. So this is heat. Use the following specific heat capacities and heat of fusion. You are given Ci equal to 2220 joule per kg Kelvin, that is specific heat of ice. Cw, specific heat of water, 4190 joule per kg Kelvin. Latent heat of fusion, right, is 333 kg per kilogram. So this all for today. Do your homework, prepare your exams, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.